constant acceleration. By the end of this lesson, we'll be able to describe the acceleration of an object, and we'll describe the position, velocity, and acceleration of an object using representations of that object's motion. To meet these objectives, we first need to understand that average acceleration is the change in velocity divided by the interval of time in which that change in velocity occurs. Averages of velocity and acceleration are calculated considering the initial and final states of an object over an interval of time. Calculating average velocities or average acceleration over a very small time interval yields a value that's very close to the instantaneous velocity or instantaneous acceleration. Near the surface of Earth, the vertical acceleration caused by the force of gravity is downward, constant, and has a measured value of approximately 10 meters per second squared. The acceleration of any object is the same as measured from all inertial reference frames. Acceleration is the state of motion where either speed and or direction is changing. The rate of change of velocity is acceleration, measured in meters per second squared, represented with the symbol lowercase a. Freefall is a situation in which an object has no external forces acting on it and is being accelerated by only a gravitational field. The gravitational field is the region of space surrounding a body in which another body experiences a force of gravitational attraction towards the center of mass. Earth's gravitational field is about 10 meters per second squared, 9.81 meters per second squared on average throughout the Earth. A derivative is the slope of a graph within an infinitesimally small change in the dependent and independent variables, and an integral is the sum of the areas between the slope of a graph and the x-axis. Those last two terms are calculus terms. If you're not taking calculus this year, you don't necessarily need to know them, but I'll often reference them, so I want to make sure that you know what I'm talking about. If an object is speeding up or slowing down, we've thought of this to be acceleration. However, when you consider the equation for average acceleration, delta v over delta t, and delta v is the final minus the initial velocity divided by the final time minus the initial time, you should notice that this is the rate at which velocity changes. Velocity is a vector, which means it has magnitude and direction. If you change either the speed, the magnitude, or the direction, there is acceleration. Also, this ratio can be represented as rise over run, as we've seen before. Nothing new here, just going into it a little bit further in depth. With the graph on the left, which is a velocity versus time graph, we see there is a constant negative slope. That constant negative slope means there's a constant negative acceleration, because the slope of a velocity versus time graph is acceleration. Here we go again. Now we have a constant positive slope in the beginning, and then a constant negative slope, and then a constant velocity, or a zero slope. Translated to the acceleration versus time, you'll see that in the very first part of the velocity, we have constant positive for some amount of time, and then a constant negative for another amount of time, and then finally a slope of zero. On the acceleration versus time graph, that means there's zero acceleration happening because our velocity is not changing. One important thing I want to make sure I point out, for this velocity versus time graph, we pass right through that x-axis. Whenever we pass through that x-axis, that means we are stopping and changing direction. Remember, this x-axis represents a zero velocity, so we start with a negative velocity and we approach zero. So we're slowing down, we stop instantaneously, and then we speed up in the positive direction. Meanwhile, our acceleration is the same all the way throughout. Acceleration is the derivative of a velocity as a function of time, which just means what we've shown. And if I add in the actual time markings on the graph, you'll see the time markings match up with what's happening on the acceleration versus time graph. Remember this old slide where we had our position as a function of time, and then velocity versus time, and then acceleration versus time. So with this, we said that the slope of position versus time gave us our velocity, and then the slope or derivative of that velocity versus time graph gave us our acceleration versus time. We started out increasing with a faster and faster slope. We started with a 0 slope, and it gets bigger and bigger, and then it's a constant slope. So we start with a velocity at 0, it gets bigger and bigger, and then a constant velocity. As we have a positive, constant positive slope for this velocity versus time, that means we have a constant positive acceleration for that same time interval. Then when we have a constant velocity, that means we're not speeding up, slowing down, or changing direction, so we have 0 acceleration. Free fall. When the only force acting on an object is the force of gravity, or when all other forces are small enough to neglect them, we call this being in free fall. When the basketball drops, the only thing affecting it in a meaningful way is going to be the gravitational field of Earth. On the left, you'll see this motion diagram. Not on the right, but on the left. Which represents a ball that is being thrown straight up in the air and comes back down. And then we'll see the graph on the right. The more we decrease the change in that slope, because our slope is changing in that graph on the right, that means if we just use a really large rise over run, that's taking an average of those velocities. Final position minus the initial position. And that's great for finding an average, but let's say we want to find an instantaneous velocity at that position. So to find the instantaneous slope, we would take the slope of the tangent line, straight line that just barely touches this curve, and then whatever the slope of that is. And essentially what we're doing is we're making the rise and the run smaller. The more we decrease the change, the closer we get to a change of 0. The slope where delta t is close to 0 would be our instantaneous velocity. That essentially is our derivative. Notice what happens to our velocity when the ball is at the top. The slope of the tangent line is 0 meters per second. Gravity near the surface of Earth always is pointed down. On the way up, velocity is up, and acceleration, which is the acceleration due to gravity, is pointed down. When velocity and acceleration are in opposite directions, we know this object is slowing down. Like that. Then on the way down, velocity is down and acceleration is down. So when velocity and acceleration are in the same direction, we know that the object is speeding up. When we plot the vertical position versus time, we get this concave down shape. And when we translate that concave down shape into the slope for the vertical velocity representation, we see that there is a constant change that's happening throughout this entire time interval. Our velocity starts off positive, our slope starts off positive, and then it goes towards 0. And then it changes and it starts getting faster again in the opposite direction. That's what our vertical velocity versus time graph is showing us in the middle. We start off with a positive velocity. It goes towards 0 velocity at the x-axis, and then increases in velocity in the opposite direction. We're getting more and more negative. Meanwhile, the slope of this line the entire time is just a constant negative slope. So that means our vertical acceleration is a constant negative. Here's our worked example. In the 1992 Summer Olympics, the German 4-man kayak team covered 1 kilometer in just under 3 minutes. Suppose that between the starting point and the 150-meter mark, the kayak steadily increases its speed from 0 to 6 meters per second, so the average speed is 3 meters per second. Part A, how long does it take to cover 150 meters? Part B, what is the magnitude of average acceleration during that part of the course? So for part A, we are given the average velocity already, and we know the average velocity is our displacement divided by our time interval. In this case, we know the displacement is 150 meters divided by the time interval, we don't know, equals our average speed. The average speed is 3 meters per second. Solving for time, we get t equals 50 seconds. For part B, what is the magnitude of average acceleration? Acceleration, a equals delta v over delta t. We know the change in velocity is from 6 and 0, or from 0 to 6, I guess, but final minus the initial is 6 divided by the time for that first 150 meters is 50 seconds. 6 divided by 50 gives us 0.12 meters per second squared, or roughly thereabout.